Okay, so let's start. And today we are happy to have Yoel Groman from Hebrew University, I think currently in Stanford, visiting Stanford, and the title is a closed string mirror construction, so please.
Okay, thanks, Jan, for inviting me to give this talk. I want to apologize, I'm kind of extremely jet-lagged still, so I hope the talk goes through well. Okay, so the title is about a construction of a closed string mirror. So let me start by first describing the setup. So the setup is we start with a symplectic manifold M, which is of dimension 2n, and it's symplectically Calabi Yau. And we have a smooth manifold, a smooth n manifold B. And then we have a Lagrangian torus fibration with possible singularities. And the singularities occur over some real codimension to stratified space. And we assume that the torus fibers are Maslov 0. And this kind of setup we refer to as a weak SYZ fibration, in the sense that we're not making any assumption about special Lagrangian. Okay, so this is close to the setting of the SYZ conjecture. Now the question is, how realistic is this? When does this thing exist? So there are examples where it's known. So basically, we have K3 surfaces, and then there is a setting of symplectic cluster manifolds, which were studied by Varl, myself. Then there's, of course, the Hitchin system, which they fit into this framework. And one expects that, in some sense, maximal degenerations of Calabi Yau manifolds should have a structure like this, though this has not been proven. It's not clearly, maybe it's only something close to this. So we don't know if we should actually expect something exactly like this. So this setup, so again, the setup is where we have a Lagrangian torus fibration, we have like a strictly codimension 2 subset where it has singularities. So this setup is kind of a working hypothesis, and in some cases it really exists. And we expect it to be something very general, but maybe it needs to be modified a little bit. Okay, so in this, by the way, if I'm going too fast, please stop me. I will be happy to answer questions.
Yeah,
so,
I think for this last point, I mean, there is this more than 20 years old conjecture of Maxim and myself that you can always construct a real integrable system essentially from maximally degenerated family of Calabi Yau. So this is pretty classical, and we demonstrated it in K3 case, and I think also Gross and Wilson. Yeah, there are some names in the story.
Yeah, so K3, I was referring to this construction, the hyperkähler rotation.
Yeah, but conjecture is absolutely general.
Yes.
Yes, so it's kind of, it's not very surprising. It's a question of a proof.
But still, it hasn't been done until now. So, yes. So okay. So in this setup, the Arnold-Yoel theorem says that if we consider the regular points of the base, the points over which were the regular fibers, then that carries an integral affine structure, which can be described by by local functions. So local affine functions are those whose Hamiltonian flow, when pulled back to M, are one periodic. Okay. So now we want to construct some mirror, and this mirror is going to be constructed over the Novikov ring. So the Novikov ring is we look at formal sums with real exponents. So this is over some ground ring. And this is a non-Archimedean normed field or ring, depending on what R is. And the norm is given by you take the maximum of e to the minus lambda I, where lambda I is kind of this like t to the lambda I, t should be thought of as some kind of very small norm. Okay, so this is the norm. And then with these, so our goal is to construct an analytic space over this Novikov ring, which is locally modeled. So the construction that I'm proposing is locally modeled on taking the maximal spectrum of something called relative symplectic cohomology, which I will review in a moment, of subsets which are pre-images of polygons, polytopes in B, which are convex. Okay, so this,
are you talking about non-Archimedean geometry in the sense of Berkovich, like we proposed, or you speak about original Tate construction? Because they're different. We say analytic of a non-Archimedean space, so it's not enough to guess in what category will be your answer.
I see. So somehow the things that we have done so far, we've done in rigid analytic, but I kind of feel like the more general story, it will be better to do the Berkovich. So I find it easier to analyze, but I think I've stated everything in terms of the rigid analytic.
Okay.
Okay, so so the notion of convex polytopes is somehow refers to the integral affine structure that I mentioned before. Okay, so of course I mentioned this thing called relative symplectic cohomology. So what is it? So let me give an overview of this invariant. So it goes like this. So suppose you have a compact set inside M. Then to this compact set, you can associate an invariant, which is denoted like so. So it's symplectic cohomology of K relative to M. And the definition is that it's the Hamiltonian Floer homology of this lower semi-continuous function, which is kind of 0 inside and infinity outside. And this is a notion like Hamiltonian Floer cohomology can be defined for lower semi-continuous functions. Now, let me say a few things about properties of this invariant. So first, it's a graded commutative non-Archimedean Banach algebra over the Novikov ring, and it has a BV structure. And then, if you have an embedding of compact sets, and I'm referring to kind of completely arbitrary compact sets, then there is a map in the opposite direction. So it's K2 to K1.
Sorry, Yoel, when you speak about BV structure on a Banach algebra, are there any foundational difficulties? Because BV, it involves some kind of derivations, something like in the Banach setting, I feel a bit uneasy. What is it something which has been worked out?
So BV is just like it's an operator which satisfies some equation.
Yeah, but BV, you see, when you speak about operators in Banach spaces, there are some analytical difficulties. Yeah, they can be unbounded and so on. So then, this is why I'm asking.
So all the operations here are kind of bounded operators. So not just bounded, like they kind of like if you apply the operator to anything, it's norm non-increasing. That's
okay. In particular, it's continuous. Okay, good.
Yes, only continue. Like everything, we're like so not just bounded. Everything is norm non-increasing. The norm is very. Okay. Okay, and then we have functorial morphisms, which can commute with all the structures, and also in the same thing that I just said, that they're all kind of strictly norm non-increasing. Now, okay, so this is some kind of something which can associate to arbitrary compact sets. But what this is good for, in particular in this framework that we want to consider, is, first of all, there is a local to global spectral sequence by Varol-Gunes. So what does it say? So consider the following setup. Consider that you take you have some compact set K, and then partition it into subsets Ki, but these should be not arbitrary subsets, but we need the boundaries to Poisson commute.
What does it mean?
Yeah, so boundaries, you should think of boundaries as being defined, as having defining functions, and you want the defining functions to commute. Okay, so somehow which particular, in our setting, we consider, say, a polytope inside B, and then we just partition the polytope, and then the compact set associated with P, the pre-image of P, we get a partition of it induced by a partition of P. That's the kind of partition we allow. So for such partitions, the symplectic homology of the compact set K is related to kind of the check complex of all these intersections by a local to global spectral sequence. So so this in particular, what this says is that if you consider K to be, you take K to be the manifold M itself, then in that case it's a fact, which I didn't mention, but that the symplectic homology of M relative to M is equal to the quantum cohomology. So this gives us some kind of spectral sequence for computing quantum cohomology from symplectic homology of some commutative cover of M. In particular, for the setting we're considering, if you take any partition of the base of an SYZ fibration, you get some spectral sequence relating quantum cohomology to symplectic homology of all these pieces. Okay, so that's an additional property. And finally, a property which is maybe not so easy to state. So the question is, how should we think of symplectic homology? So if we take the chain complex, then at the chain level, it should be considered as a deformation of some module, which is free generated by like some lambda nov module, which is freely generated by the chains on K and by the Reeb components. So when you have a compact set, at least if you consider, you have to assume that the compact set has contact boundary, and maybe in so let's say with isolated periodic components, then in that setting, somehow there's an invariant here which involves M and K, but somehow the generators of this complex they only care about K. They have to do with the periodic orbits on the boundary and the chains inside. And then there's some differential which kind of that gives us this deformation. And yes, so of course we're associating with each Reeb component we are associating some chain complex which In general, it's just something which can be called kind of the infinitesimal Floer cohomology near gamma. But if gamma is a Morse-Bott component, it's just the chains on gamma, maybe twisted by some local system, which in all the cases that we care about is trivial. Okay, so in other words, you should think of it as being something generated by chains, by singular chains inside, and Reeb orbits on the boundary.
And how do they interact? Sorry for the stupid question. Because it's a direct sum, there should be some interaction between these Reeb orbits, probably in the end. Yeah.
Yes.
You're
saying what? So what is the complex? So the complex means we have Reeb orbits, and then the chain complex is the differential is given by looking at cylinders which solve Floer's equation. Is that the question you were asking?
Yeah, that's part of it, but either other higher structures, because Floer is just the first step, and for the cohomology, that's it. But other higher
structures. So other structures. So for example, the product comes from counting pairs of pants.
Yeah, just in the standard way. Okay.
Yeah, the standard way. Yeah. Yes. I was kind of trying to just emphasize the non-trivial point. Like the non-trivial point is to say, because it's not obvious from its construction that it really is like that somehow these are the generators in some sense. But yes, it's okay. So let's see what does this give us in examples which matter. So if we are considering a polytope, which is a subset of B-reg, and if it's an integral affine convex polytope, then the chain complex is in this case a deformation of just, you think of the as a module, you have it's freely generated over the Novikov ring by the I think I should have said homology, but I'm not sure. So let's say I just look at the zeroth part. So SC0M is just freely generated by integral homology classes of this, which is basically a torus. Okay, and the point is, because where do you get Reeb orbits from? You get them from maybe you look at this polytope, you maybe make it a slight smoothing, and then you look at so Reeb orbits correspond to integral affine covectors, which support this domain. Okay, so these are the generators are something are this, and then now we ask, how does it depend on M? So if M is the Liouville completion of the domain, so which means whenever you have a Liouville domain, you can just complete it. So if you have this polytope, it's the preimage of the polytope is just a product of P with the torus, and then you can complete it into the cotangent bundle, and then this is something which is completely computable, and you find that if you compute the symplectic homology, you just get the algebra of analytic polyvector fields on I need to write on. Let me write this in a second. On a certain subset of lambda star to the n, which is given by the valuation by the map.
Sorry, K is KP in this answer, or what?
Yes. KP, and here it should just say that, say, x1 to xn goes to, I don't know, minus log of the norm. Okay, so this is the answer when you just have this Liouville domain, but then when you consider it inside some manifold, which means that we're not looking at the completion. So then we have to kind of consider that there are certain Flirt differentials which go around the manifold, and maybe they deform this, and this is something which we need to control. Okay. Okay. So this is this invariant, and okay. So are there any questions?
Well, it's all very fast, but
maybe I should go
those who
slower.
knows the story over complex numbers, it's kind of not surprising, but for people who see it first time, I don't know.
Okay. So maybe I should go slower, or please ask me questions, or
yeah, okay. So that's to the audience. Please ask questions.
yes.
Yeah, anyway, go ahead. If
Okay.
people are silent, then I don't know the reason, but maybe they understand everything.
Maybe I've lost everyone already.
Well, there are two options, optimistic and pessimistic. So
as usual. Yes. Okay. Sorry. Yes. Okay. So this is some invariant. So we can associate this invariant given the setup that we started with, where you have a Lagrangian torus fibration. You have these nice algebras which you can associate with convex polytopes in the base. Okay. Okay, so now this leads to the following construction. So back to the setting that we started with.
Maybe because I see some graduate students here anyway. So if you consider a single piece, just one convex polytope, and look for the piece of the whole integrable system, let me call it this way, or this polytope. So what's the mirror? What is the mirror dual to this piece sitting over a single polytope? Maybe it's
okay. Yeah. So the mirror dual. So you should think of this. So if it were over C star n, and suppose like that M is like really the completion. That's what you ask, right? So in about this case, then the mirror really is just a toric domain. So it's a subset. So for example, if you were to think of lambda stars just C star, then it's really just the toric domain, which lies over P. So for example, if you just consider a square, then it's just the set of points whose absolute value falls between some numbers A and B. So it's real. So if it's a square, it's a poly. It's kind of a product of two annuli. Okay, so that's what. So that's the picture, at least if you know that you have no deformations.
Okay. Any questions from the audience? Yeah, because it's sort of a standard SYZ picture.
Yeah.
Okay, probably it's clear. Go ahead. Yeah.
Okay. So now we want to construct the closed string mirror. So something which is based on this SH0. So we start with the setting that we formulated. So we have the weak SYZ fibration. And then for each polytope, we write, so we're going to look at, SH0. So SH, which we discussed before, is kind of a graded ring. And we look at the 0th piece. And so what we get is we have some pre-sheaf of rings over the Novikov ring on the base. That's what we have. Some pre-sheaf of rings. And actually, typically, in the settings we care about, it's a sheaf and if you say the word sheaf, you have to say which topology. So open sets are finite unions of polygons. Okay, so that's a construction. Sorry, that's something which you just have associated with this base, and then given an algebra over the Novikov ring, you can denote kind of the set of maximal ideals of this algebra by you just take so this is denoted by MA, and given this, you have some kind of completely formally, you can just define a set, and this set I will call it the mirror dual of M, and it's just a set, and it's a union of over all points in the base of the set of maximal ideals of this ring, which is associated with each point. Remember, we said that like every compact set has a you can associate with it a ring. So particular point is a compact, like the preimage of a point is a compact set. So this gives you a set, and obviously just from the construction you get a projection to the base. So starting with the setup of a weak associative fibration, we've constructed a set with a fibration over the same base, and we want to somehow discuss when does this give us the mirror. So this leads to a host of questions. So first, when is it like, okay, we constructed a set, when does it carry some natural structure of a rigid analytic variety? When do you know if it's smooth? Is it Calabi Yau? Does it satisfy enumerative mirror symmetry? Does it satisfy homological mirror symmetry? So these are all questions, and I think I will only talk about the first question, but all these questions are at least something smart can be said about them. These are not just questions up in the air. But I'm going to discuss the question of kind of constructing, going from a set to like when at least some general conditions for when this is actually a rigid analytic variety.
Can I? Sorry, I'm sorry. I came a little late. So what are the assumptions on a base B?
Okay, so I have so for this definition, the only assumptions were that you have a Lagrangian torus fibration, and the base B, there's a subset delta, which is of codimension 2. And there's something I didn't quite say, but you also have to assume either that it's somehow M is closed, or that M is, if it could be an open manifold, but then it has to be geometrically bounded. So that is something I didn't mention, but these are the assumptions.
So like in terms of examples, do you know anything except for like a K3 case?
Yes. So the set of examples. So first, I think the Hitchin systems, that's one set of examples. Like I think every Hitchin system. But now there's the set of examples like Umut and I have written about something called symplectic cluster manifolds. So they're still in dimension 4, but there are kind of analogous constructions to these symplectic cluster manifolds in all dimensions. So there are lots and lots of examples, and it's kind of expected that maximal degenerations of Calabi Yau manifolds should give something like this. Okay, so this is the construction so far, but I've just constructed a set with a projection. So later, when I want to kind of say that this is nice in some way, I will have to add some assumptions about what types of singularities are allowed.
Okay, thank you.
So of course, before we kind of consider all these questions, we have to look at the stupidest case, like not the simplest case, because usually it contains everything. So in the particular case that we already spoke about, where M is the cotangent model of a torus, and the Lagrangian torus fibration means is projection to the fiber, and we do the maps that we've described before, then in that case everything is computable, and as I already said, this is that the zero symplectic homology is really kind of the ring of analytic functions, and everything is natural with respect to restrictions. So this construction really has the structure of a rigid analytic variety. So this is okay. So this is now a more non-trivial case is in a paper of Umut, Raugunas, and myself, we considered the case of two-dimensional symplectic cluster manifolds, which to describe them, what they are is basically you consider you have Lagrangian torus fibrations over R2, and you allow focus singularities, and there is some completeness condition. So the completeness condition is that somehow if you start from a point and you go in any direction, then as long as you don't hit some eigenray, then you can just go on forever. And so for that, for that setting, we proved that M check, the set that I just discussed, is a rigid analytic variety, and it's smooth if kind of whenever you have a focus singularity, you can have multiplicities. So the statement is that it's smooth if the multiplicities are 1, and then this map that I described, which to the base, is a non-Archimedean SYZ fibration, which just means that locally over the regular points, it's modeled on the map from lambda star n to Rn, and it carries a canonical Calabi Yau form. Okay. So that's a setting where there's an answer and it's on the archive. So any questions about what I said so far?
I mean, this general philosophy is very old, and there are some kind of it all goes back to our paper with Tim. So and there are some examples, but the general story I think has not been worked out.
Okay.
Yeah.
So this is okay. So now I want to say something about the general story. So I will state two things which are almost theorems, and I say almost theorems because there's something which requires I believe is true, but which requires some technical work. And I hope maybe if I get there, I will explain what is the point that's still missing. So the almost theorem is almost theorem 1 refers to what happens for the regular fibers. So now I'm talking about just the setting that I said. So which basically the assumption is that somehow the manifold is geometrically bounded, and that you have the singularities occur as codimension 2 sets. So suppose that generic rays in B continue indefinitely, which means that for a generic direction, you can go, like when you construct an integral affine structure and it rises in some natural way, often it's not entirely clear what kind of, you can't just assume that it will be complete. So this is an assumption you have to put in, that in generic directions, you have affine, your rays go on, continue indefinitely. Then if you restrict attention to the pre-image of, so you take this set that we defined before and you consider the pre-image over of the regular part, then this is a rigid analytic space, and pi check is a non-Archimedean SYZ fibration. Okay, and this in many cases it's actually a theorem. Okay, but yeah. So what I want to talk about is what about singularities? So what happens if you have what happens over the singular points? So, but before I go further, please ask me questions. Okay, so let me. Okay, so we need to define. So I'll continue. We need to define what is what is an admissible local model for a singularity. We cannot, at least we don't have the technology to just deal with arbitrary singularities. So I will impose a bunch of conditions. So okay, so what I'm going to say is let's focus on let's talk about local models. So let's focus on neighborhoods of a singular point. Okay. So an admissible singularity will be a model which has some weak SYZ fibration from some compact set to some set P, and we require the following things. So first, we require that K is a Liouville domain, and the more precise thing is to say that we have an Euler vector field on P, which is well defined. So basically, there's a scaling action which the integral affine atlas on the complement of the discriminant locus commutes with. Okay. Then we want that if we take there's a notion of Liouville completion. We have this kind of fibration over the cone of this polytope. And we want this to be geodesically complete. And maybe this is automatic, I don't know, but let's make it an assumption. And then we need some kind of convexity assumption. So we want that we need that this P is rational, polyhedral, and convex, which means that it's an intersection of a finite number of integral affine half spaces. So, for example, you have some focus singularity, but you can define away from the singularity. You can have various lines, affine lines, which divide the space into half spaces. So he wants an intersection of such integral affine half spaces. And note when you go up a dimension, so say in 3 dimensions, these integral affine half spaces will have to meet some singular point, but still you can have integral affine functions which are defined even at the singular point. So it makes sense to talk about this kind of polyhedral convexity. And then there is an assumption about how the classical, so there's a map from the classical cohomology of K, where K here is Kp, so it means we're looking at the Liouville domain, and we want that the map, at least in degree 1, we want the map from the singular cohomology to the cohomology of the generic fiber. We want it to be injective in degree 1. Okay, so then we can state almost theorem 2, which is also in progress, that if pi is locally modeled on admissible singularities, then there is we can construct a rigid analytic the structure, like we can construct kind of a rigid analytic atlas for M check, so that pi check is a non-Archimedean SYZ fibration. And now the local version, namely, this is already interesting, even if we talk about, if we take M to be the completion of the Liouville domain. So now we're talking about some neighborhood of a singularity, and so we're talking, and we're looking at the manifold, which is we just have the completion of this singularity. And so in particular, we're looking at something where the symplectic form is exact, So when the symplectic form is exact, this is a theorem, a theorem in progress. So it's not yet uploaded, and we're still, so hopefully I'm not misleading. So like the thing which I said that there's an almost theorem has to do somehow with non-exactness. There's something to still be overcome. And also if we apply this construction, we just take some K3, which we've constructed a Lagrangian torus fibration for, and we apply this construction, then in that case, this is all, we don't have to worry about what I'm saying about that this theorem is still, like there is still a point to settle, which I'll try to explain within the proof. Okay, so this is the statement of the theorem.
Yeah, I am a bit so confused. First of all, you impose some restrictions on the singular locus, and from the very beginning of SYZ, this was the only problem with SYZ mirror symmetry. So my question is about examples beyond the four-dimensional story. And second question is that as a K3, if I remember correctly, we did it with Maxim exactly.
Yes. Okay, so let me answer both
mirror, so I'm confused. What is in progress?
Yes, let me answer both questions. So so the question about existence of examples. So there is an issue with so for example, if you look at singularities of Gros-Seibert type, then so let's say the positive singularity satisfies these conditions. Then there is the negative singularity. There's a problem that or there used to be a problem that somehow there were constructions where you had something which is only so there were constructions where it was only you didn't have strictly codimension 2. So there is a work by Johnny Evans and I forgot the other name, where they show that this can be made into, there is a way of making this into strictly codimension 2. So I think, what?
Evans Maury.
Yes. That's one answer. And then, just like I said about the symplectic cluster manifolds, you can construct examples in dimension 3 or in any dimension, which are not cluster manifolds, but kind of very similar, where you only use positive singularities. So there are lots of examples of open manifolds that you can construct, which have these. And otherwise, as I said in the beginning, I'm just imposing some kind of, I don't know, I don't have like a general answer of how realistic my assumptions are. Now, with regards to the second question, so
the second question was that you wrote something about K3.
Yes.
If it's the same K3, which
it's the same, yes. So
what
the question is, what is the problem? So the question is, what is the problem you're trying to solve? So if the problem is trying to solve is to construct a manifold, then probably this is just another construction of the same manifold. But if the problem is you're trying to solve is, say you want to prove enumerative mirror symmetry, or you want to prove homological mirror symmetry, then how do you know that, like, if your construction is done by combinatorics, then how do you know that it in any way encodes any information in holomorphic curves? So this construction, I go back to, I mentioned like the Varolguna spectral sequence. So if you construct a manifold by using Floer theory, then so you can construct not just this manifold, this closed-ring mirror. You can this requires a little more work. You can you have the higher symplectic homologies, and they give you sheaves of polyvector fields. And supposing with some additional work, you also have some Calabi Yau form, then this gives you kind of a direct relation between the quantum cohomology on one side and the RAM cohomology on the other side, and maybe this can be pushed further to create a proof of say enumerative mirror symmetry. So the goal is to have some kind of construction which is directly related to Floer theory and has so in such a way that it somehow will be clear why this should satisfy homological mirror symmetry, or why it should satisfy enumerative mirror symmetry. About the realism of the assumptions, what can I say? I think at least insofar as Gross-Siebert singularities are realistic, I think these assumptions are realistic. That's what. Is that a satisfactory answer?
Well, not for me, but yeah, because I don't know. We offered with Maxim long ago this in the case of K3, but actually it was just more general. We simply proved it for K3. Construction of a functor, so it was almost homological mirror symmetry, I would say. Yeah, and so maybe if you add your assumptions, it will be just the same technology will give a proof. Yeah, and as for enumerative side, there is this industry actually developed by Tony Yu, which is a direct way to count curves by methods of non-Archimedean geometry. So it's much more advanced than what we did with Maxim long ago, and I think it will work nicely. So I don't know what Gross and Siebert assumed, but this non-Archimedean technology actually in Berkovich setting, because the state is I think it's inadequate because it's a wrong topology for the mirror dual. I mean, it's totally disjoint. So anyway, so
what? Sorry, I didn't know. What was the last comment?
No, the last comment is about this Berkovich non-Archimedean geometry is really essential because the base of your fibration, it's simply it's a skeleton. Now it's called, fortunately, essential skeleton. And so then you can compute enumerative invariance and even some categorical structure just entirely in terms of the skeleton. So Berkovich did it long ago, but in a slightly different setting, but the idea was essentially in his paper that have some non-Archimedean space in the sense of Berkovich. Inside you find some sub-variety, or rather there is a map, continuous map from this non-Archimedean space to some real sub-variety. In your case, it's B. It's a base, including the singular set. So then Berkovich picture is that over outside of the discriminant, it's a non-Archimedean torus fibration. And so then the problem is what to do with the discriminant, but you impose probably quite restrictive conditions. And so maybe you can kind of derive everything by looking at the non-singular part. Yeah.
Okay, so the only thing I can say is I don't know how, like, there is an advantage in a construction which uses symplectic topology, like uses Floer theory rather than combinatorics. But
It's not combinatorics. It's, have you read our paper? It's all Floer theory. We consider the generation of pseudo-holomorphic disks and so on. And I mean, this story was tropical geometry and started from that. And it's part of a non-Archimedean picture, yeah. Because you draw some curves on the skeleton of your non-Archimedean space. So it's not combinatorics. Whatever Gross and Zibert do, it's what they think is correct. But non-Archimedean technology, it's kind of more powerful. It's not combinatorics. Yeah, but anyway, okay, go ahead.
Okay, so it's maybe this is just a different proof of an old result. Yeah. Okay. So yeah, so let me try to explain the proof. So yeah, so the proof of so I guess I will only get to discuss the proof of the first theorem, which is about what's going on over the complement of the skeleton. And there, the point is that we need to know, we need to somehow be able to control the deformations of so we said, like, what we have is we have some say we're looking at the neighborhood of a polytope, and we a priori what's going on. Let me look at there's a picture here. So you have some so say you have some Liouville domain K, and this Liouville domain is contained inside some maybe a closed symplectic manifold or some general symplectic manifold. Then the contributions to the Floer differential there are two types. So there are contributions of things which stay inside, and so these are kind of invariants only of K. And then there are contributions from things which go outside, and these are invariants of the embedding. And one can measure them. So any curve contributing to the Floer differential represents a class which is relative to K. Now, if you pick some primitive for K, some primitive lambda, then you can evaluate, you get some relative class that you can evaluate on these curves that go outside. And now it turns out there's some integrated maximum principle which says that if we look at the curves that go outside, the evaluation of this relative class is non-negative, and in fact there's some positive constant, so that it's actually greater than some h bar. So basically we can consider whenever we have a Liouville domain inside the bigger manifold, we can consider the symplectic homology relative to the manifold as a deformation of the symplectic homology relative to its own completion. And this gives rise to some spectral sequence which measures the deviation from the Floer theory of this subdomain of being local. Now, in general, this spectral sequence does not really compute, is not somehow, it could be that somehow the deformation is too big relative to the differential coming from the curves that are inside. And in that case, the spectral sequence doesn't help us. So there are examples. So if you consider a disk inside a projective space, and if this disk contains a hemisphere, then the symplectic homology of the disk relative to its own completion is 0, whereas the symplectic homology relative to CP1 is can be shown to recover quantum cohomology. So So one needs to exercise caution, but it turns out that if the norm of some right inverse to the differential is equal to 1, and we know that the spectral sequence degenerates on the first page, then we do get some kind of non-canonical isomorphism between the symplectic cohomology relative to its completion and the symplectic cohomology in the embedded setting. Now, the first of these holds for all the local models that we care about, but I want to show that the second, that somehow the spectral, that the spectral sequence degenerates, and this will tell us that symplectic cohomology of a neighborhood of a torus fiber is non-canonically isomorphic to symplectic cohomology to the symplectic cohomology relative to completion, which we computed before. And let me try to give the general idea of why this is true. And this comes from some geodesic completeness assumption. And this implements an idea by Sheluchin, Tonkanog, and Vienna. So this deformation, you can measure it by a number which I call tau, and it's the infimum of the valuations of the relative class omega lambda to Floer trajectories u, which contribute to the deformation. Then one can show that tau depends only on the skeleton of the domain with respect to lambda, which in our case means a choice of some focal point for P. So which in other words means that this deformation is a function from the base of the SYZ fibration to R. So that's one thing. The other thing is, if we shift this focal point, so P here means the point, not the, then that amounts to amounts to shifting the primitive in some way, which means that this function, if we consider it as a function on the base, it's an infimum of affine functions. And so an infimum of affine functions is concave. And moreover, this we said before that this function is non-negative. Now, if you have a concave function which is non-negative and its domain of definition is a line, then this function has to be constant. So because a non-constant concave function cannot be positive. So this means if there is some deformation, we can measure it by some number, and this deformation has to be a constant function in B. And then in order to conclude, we need to be able to show that this constant is actually infinity, and then there is no deformation. So how can we have a contribution where tau is constant? It must come from curves whose boundary is null homologous, and for these, so in the exact case, you can show that you can't that such a thing implies that the cohomology is zero. So in the exact case, we conclude that this is that there is no deformation, and otherwise we need some kind of SFT next stretching argument, which this is the point which is not yet settled. So there is an SFT next stretching argument which should show that in complete generality that this tau is infinity. So this means that as lambda modules, we get a non-canonical isomorphism between the symplectic homology of Kp relative to M and the symplectic homology of Kp relative to its completion. And this means that so it's kind of commutative. So as a commutative algebra, we know that this is the Kp relative to its own completion is a completion of Laurent series. So this implies that SH itself relative to M is also a completion of Laurent series. So this shows us that we have some of the symplectic homology of some thickened domain is actually an apinoid, and then it remains to show that somehow the map for symplectic homology of a polytope to the symplectic homology of a fiber induces a bijection between kind of this and the maximal ideals of symplectic homology of Kp. And this one way to deduce this, and this is where I have to stop, is also by somehow you can show that somehow this non-canonical isomorphism can be made into an isomorphism of the sheaves. And I guess I will stop here.
Thank you very much. So questions? Yeah, this last part was very nice. So it's idea somehow resemble this Hartog's principle. So you want to extend something to a singular set, but yeah, so it's I'm not sure about whether it's proof of something old or something new, but the idea is good. Yeah.
Okay.
Yeah. Yeah, I like it. Okay. Questions? And this is mostly your joint project with Varalgunis, or it's your own?
Umut and I, this thing we discussed a lot with Umut, but somehow we decided for parts of this project that each one, he has his own ideas, and so each one of us is doing some version of this.
Yeah. So, but a kind of from a very general perspective, do I understand correctly that you take some kind of maybe I don't know, contact boundary of the neighborhood of the pre-image of some neighborhood of the singular set, and then use SFT in order to construct the mirror dual affinoid domain? Is it?
You're asking how do I do it for neighborhood?
No, I mean just conceptually, yeah, because there are some details which you explained, but conceptually you have kind of, as everyone, the easy part, which is a complement of the discriminant. And so now, whatever you say, you simply just say that you take symplectic homology of the fiber. Yeah, that's what you. Okay, but now you should handle somehow the neighborhood of the discriminant. With
So the neighborhood of the discriminant locus. Let me say very briefly. So in this case, I kind of described even if it's a neighborhood of the discriminant locus, you still have some kind of structure on you understand what are the generators of the complex, and they also correspond. They have some kind of this nice description in terms of you have for each say for each corner you have some cone of monomials and so on. And basically, the point is to somehow prove that you also don't have a differential inside. And that uses somehow, so for example, in dimension 2, you know that you don't, so you know that somehow all of these, say you look at neighborhoods of the edges, so for all of these, you know that you have somehow there is no differential because these are neighborhoods of tori. So now so you know that the map at the level of generators, the map from from kind of the chains of the full domain to the direct sum of these boundary domains, you know that that map is injective, and that kind of allows you to deduce that you don't have an interior differential. So this is a proof in dimension 2, and then you kind of proceed inductively and show that for all these modules, you don't have a differential inside, and that more or less allows you to conclude that somehow with each face, that these are algebras which have kind of a generator associated with each face, and such that the restriction to each of these neighborhoods of the face is a kind of an inclusion of Laurent domains. So that's how this.
Mm-hmm. Yeah, good, nice. Okay, still, let me ask again other questions. Well, if not, then thank you very much for the talk, and this is it for today.